Today we're going to look at another important function called the unit step function. So we've drawn it out here graphically and also written it in mathematically. So graphically you can see that this function has a value of 1 whenever t is greater than or equal to 0 and a value of 0 when t is less than 0. And this is it written out mathematically. You usually see it called u of t. So u of t equals 1 for all t greater than or equal to 0, and it equals a value of 0 for all t less than 0. The only thing to note in this is that whenever t is actually equal to 0, it's defined as a height of 1. So it's defined at that 1 point there, and it's not defined at this point here. So in order to find the Fourier transform of this, we're going to go and split this into its even and odd components, and we'll work with the even and odd components in order to work out the Fourier transform. So the even component of this is going to be a value of a half. The odd component is going to be a value of minus a half and plus a half. Now there's another function called the signum function, which is a value of minus 1 and plus 1. So you usually see that written as SGN. So what we have here is half of that. So that's a half of that signum function. So then we can say that this function u of t is given by the summation of these two here. So you can see if you add this section here to that section there, you get minus a half plus a half will give you the 0. If you add this height here, which is a half, to this height here, it gives you a value of 1. So we can say that the function u of t is equal to a half plus a half signum t. So we'll use this now in order to work out the Fourier transform of the function u of t. So in order to find the Fourier transform of the unit step, we're going to have to find the Fourier transform of the function a half plus a half signum t. So let's look at the Fourier transform of the signum t function first of all. Now the signum function is defined as minus 1 when t is less than 0, it's 1 when t is greater than 0, and it's defined as 0 when t equals 0. Now we can't find the Fourier transform of this because the Fourier transform doesn't converge, because this won't be absolutely integrable. Now we don't want to go through the details of that here. If you're interested, you can always drop me a line and ask a question, we can cover it somewhere else. But the point is that we can't use this in order to find the Fourier transform. But what we can do is we can use something that's an approximation to it. So if we were to take this function e to the minus epsilon t when t is greater than 0, this is a function that looks like that, and that's a point 1. And the other function here is minus e to the epsilon t when t is less than 0. So that's this function here, and that height there is 1. So you can see here, as this value of epsilon tends towards 0, well that whole thing there would tend towards e to the minus 0. N at the power of 0 would be 1. So that tends towards this straight line of height 1, a straight line of height 1. So this looks very similar to the signum function. So what we're going to do is, if we call this new function here g of t, we can say that as the limit as epsilon tends towards 0 over g of t, this function will equal the signum function. So we're going to use these functions here in order to find the Fourier transform of the signum function, and we'll do that in the next slide. So let's look at the Fourier transform of this function here analytically. So we had the function split into two. The function was minus e to the epsilon t from minus infinity to 0, and the second part of it was e to the minus epsilon t from 0 to infinity. So we'll form the Fourier transforms of both of those. So we simply multiply one by e to the minus I omega t by dt and integrate, and our one by e to the minus I omega t by dt and integrate, and that gives us a Fourier transform. So we can take out the negative sign out of this one here, and we can put the common factors in here of t, so we'll end up with e to the epsilon minus I omega t by dt, and we can take the negatives out here, and we'll have negative epsilon plus I omega t by dt. Now when we do the integration here, we've seen before, all that happens is the exponent here comes down below, and we've left with a negative sign out here, so we'd have minus 1 upon epsilon minus I omega, and of course that's going to be multiplied by e to the epsilon minus I omega t, and the limits would be from 0 to infinity. So I'm not going to do that. You can go ahead yourself and put the limits in, and you'll find out that you'll just be left with this term here, minus 1 upon epsilon minus I omega. Now the same for this here. This side here comes down, you would have 1 upon minus epsilon plus I omega, and whenever you took the limits would be from 0 to infinity. So if you put the limits into that, that'll give us a 1 upon epsilon plus I omega. Now don't take my word for that there, I've worked through that in a piece of paper and it does work out, so I suggest you put the full limits in and get this answer for yourself. Now what we said before is we're going to take the limit as epsilon tends towards 0, because if we do that, then this function here with these two parts will tend towards our signum function. So we see here, we just take the limit as epsilon tends to 0, so as epsilon tends to 0, then that whole thing tends to 0, just left with a negative, and negative will cancel out, so you're left with 1 upon I omega. The same here, as epsilon tends towards 0, you're left with a 1 upon I omega. So when you add both them up, you end up with the value of 2 upon I omega, but if we were to, when we divide by I, it's the same as multiplying by negative I, so we can take that I up and it becomes minus 2 I upon omega. So if you're not sure why it is that when you divide by I it's the same as multiplying by negative I, then just remember what I is. I squared equals minus 1, and then you could work that out for yourself. So what we're left here with then is the Fourier transform of the signum function is going to equal minus 2I upon omega. So we can see how this is going to look if you think about a function. Let's say here is we've got I omega and we've got the function of I omega, and this is function here is shown I upon omega. So all we're looking at here is as omega tends off towards infinity, then this whole value here, I upon omega, is going to tend towards 0. And whenever the value for omega tends towards 0, this whole thing's going to tend towards 1. Okay, now the same we can say whenever we look at the minus I upon omega, and we can work through that, and we'll see we'll get a graph that's going to look something like that. Okay, so this here is roughly what the Fourier transform is going to look like. Now what we'll do is we'll go and we'll put it in MATLAB and we'll actually see it in MATLAB. Okay, so this is the output from MATLAB of the Fourier transform of the signum function. We will look at this in MATLAB just in a second, but this is a signum function in the bottom line here, and this is a Fourier transform of it in the top line, and you can see it's a purely imaginary function. There's no real parts, so there's no vertical parts on this function here. So let's have a wee look at it in MATLAB. So we'll use this function again, f1.m. This time we're going to put in the signum function. So the signum function is just given by sign in MATLAB. Again, it's in the quotation marks, and we'll do it from minus 10 to 10. Again, this little equation here is available to you in a text file in the resources section. So whenever we run that, we get what we'd seen in the previous slide. So we have our signum function here in the bottom line, and we have the Fourier transform of the signum function, and you can see that the Fourier transform is a purely imaginary function. There's no real part to it. So we're now in a position to work out the Fourier transform of the unit step function. Now we know the unit step function can be written as a half plus a half signum t. So we'll look at the Fourier transform of these separately. So we know the Fourier transform of 1 is 2 pi delta omega. We've seen that when we looked at the impulse function in the previous video. So it means that the Fourier transform of a half is simply a half of that, so that will be pi delta omega. So that's one part of it. Now we know that the Fourier transform of the signum function can be written as 2 upon I omega from the previous slide, but this is going to be simply half of it. So rather than have 2 upon I omega, it would just be 1 upon I omega. So we've drawn these two functions out here, and the Fourier transform of the step function is simply the addition of these two. So the Fourier transform of the step function is pi delta omega plus 1 upon I omega. So whenever we see it graphically, which we will do just in a minute when we get into MATLAB, we'll see this function here and we'll see the delta omega, and it's really quite interesting to see how both of those come together in one 3D graph. So we use the same file f1.m in order to look at our unit step function. Now, our unit step function is called the Heaviside function, so we write it as Heaviside t after Oliver Heaviside, one of my favourite engineers and scientists. And we'll go again from -10 to 10. So let's have a wee look at the output. So here is the step function, goes from 0 to 1, and you can see here I've got the frequency axis, an imaginary axis and a real axis. So it is a complex function here. It has a real and it has an imaginary part. So if we look at the real part first of all, so the real part there is tending towards an impulse. So that in effect is our pi delta omega. So that's the even part of the Fourier transform. In the time domain, it's equivalent to the factor of a half. Now if we were to look at the imaginary part, there's the imaginary part here, and this is the odd part of the Fourier transform, and it's given by our 1 upon I omega. So it's interesting to see how we've got the two parts of that Fourier transform wrapped up in this really neat looking three-dimensional image. So that's all for this video. Thank you for listening and goodbye.